Hello everyone, this is the fourth lecture in week 7. So, recall that in the last 3 lectures we learnt about quadratic penalty method, which is an algorithm to find the critical points of a constraint optimization problem, specifically a nonlinear programming problem. So, we mentioned that the quadratic penalty function associated with a constraint optimization problem has a certain form, right. So, you have the objective function plus gamma into the square of the equality constraints, right. So, when you have only equality constraints, right, and we started with what we do when you have only inequality constraints, right. So, recalling what we did. So, when the constraint optimization problem has only inequality constraints, the associated quadratic penalty function q of x comma gamma is defined as f of x plus gamma into summation I equal to 1 to p max of 0 comma j of x the whole squared. So, why is this the case? Because if g of x is less than or equal to 0, we want the penalty to be 0, and if it is greater than 0, yeah, we want the penalty to be greater than 0, right. So, that is the reason we write it as max of 0 comma g of x. Okay. So, one other way of writing this is f of x plus gamma into summation I equal to 1 to p g of x plus the whole squared. Okay. So, this plus denotes max of 0 comma g of x, that is because it is just the positive part. So, if it is negative it is 0, if it is positive then it is equal to j of x, right. So, this is a notation which is used often in the literature, and we will stick to this notation. Okay. And I also mentioned that there was an issue when you have inequality constraints, and what was that? The gradient is clear. I mean, you just have del f of x plus 2 gamma summation I equal to 1 to p max of 0 comma j of x into del g of x. Okay. So, the summation is for the whole expression. Okay. So, this is this has no problem, because g of x less than 0 and j of x equal to 0 gives you the same expression for the gradient, but that is not the case with the Hessian, right. So, when you take the second order derivative, you can see that when g of x equal to 0, the Hessian is different when you come from less than 0 to the one that you have when you come from greater than 0, right. So, the left hand limit and the right hand limit are not the same. Okay. So, this q is actually not twice differentiable. Okay. But it turns out that when we use Newton's method to minimize q of x comma gamma in quadratic penalty function, right. So, many times it actually gives you the right answer, though you can mention it as the Hessian of f of x plus 2 gamma j of x into Hessian of j of x plus 2 gamma del g of x into del g of x transpose, right. So, the last term I mean it comes only when when you come from g of x greater than 0, it does not come when you have when you come from g of x less than 0, but nevertheless when you give this whole formula you get the answer usually. Okay. All right. So, yeah, this is just a recap of what we did at the end of the previous lecture. So, we will now look at an example and also give the Python code for the same. Okay. So, let us consider the following example. So, let us minimize half x1 minus 3 the whole squared plus half x2 minus 2 the whole squared over x1 x2 of course, subject to the following inequality constraints. One is x1 greater than or equal to x2, the other is x1 plus x2 less than or equal to 1 and the other is x 2 greater than or equal to 0. Okay. So, we want x 2 to be non negative, we want x 1 to be greater than or equal to x 2 and we also want x 1 plus x 2 to be less than or equal to 1. Okay. So, if you actually see this pictorially or geometrically, okay. So, you get the following constraint set. So, let us say this is x 1 and this is x 2. Okay. So, x 1 greater than or equal to x 2 is this region. So, the one right of the line that I drew now. Okay. So, this is x 1 equal to x 2 and x 1 plus x 2 less than or equal to 1 will look like this. So, yeah, so the one to the left of this. Okay. So, this is x 1 plus x 2 equal to 1. Okay. And x 2 greater than or equal to 0 means yeah, so it is above the x 1 axis, right. So, x 2 equal to 0 is the x 1 axis. So, yeah, anything above the x 1 axis is x 2 greater than or equal to 0. So, the constraint set is defined by this particular triangle. Okay. So, this is 0 comma 0 that we know, this is 1 comma 0, okay, and this is half comma half. Okay. So, that is the point of intersection between x 1 equal to x 2 and x 1 plus x 2 equal to 1. Okay. That is easy to see as well. I mean both the lines intersect at half comma half, right, and x 1 equal to x 2 intersects x 2 equal to 0 at 0 comma 0 of course, and x 1 plus x 2 equal to 1 and x 2 equal to 0 intersects at 1 comma 0. So, these are the vertices of the triangle 0 comma 0, half comma half and 1 comma 0. Okay. So, that is the constraint set, but and now what are we minimizing? We are actually minimizing the distance between the point 3 comma 2 and yeah, this particular constraint set that I have just drawn. Okay. So, writing in words, it is we want to minimize the distance between 3 comma 2 and the constraint set which is the triangle with the vertices 0 0 0 0 half half and 1 0. Okay. So, yeah, that is basically what you want to do, and just from the figure it is clear that, so 3 comma 2 is somewhere here. Yeah, I mean pointing it out is hard, but yes, should be somewhere here for example. I mean yeah, since there is no gap I am just giving an x mark here. Okay. And I mean it is easy to see that 1 comma 0 is the closest point, right. So, since I mean so there is nothing beyond this circle. So, if you draw a circle starting from I mean with 3 comma 2 as the center and passing through 1 comma 0, right, you can see that the whole constraint set is to the left, right. Of course, I mean this can be derived analytically, but since it is easy to see from the figure I am just giving you that the answer is 1 comma 0. Okay. So, yeah, x star is actually 1 comma 0. Okay. And so, yeah, we will try to solve this using the quadratic penalty function which we just gave in this page, right. So, we write q of x comma gamma as this, okay, and try to solve it using the quadratic penalty function. So, let us first write down the quadratic penalty function properly. That is going to be q of x comma gamma equal to f of x is half x 1 minus 3 the whole squared plus half x 2 minus 2 the whole squared plus so you have 3 inequality constraints and each of them needs to be written as g of x less than or equal to 0, right. So, x 1 greater than or equal to x 2 I will write it as x 2 minus x 1 less than or equal to 0. Okay. So, this will become gamma into, so the first constraint is x 2 minus x 1 less than or equal to 0, and you need to take the positive part. So, I will write it as plus and squared. Okay. So, the second one is x 1 plus x 2 minus 1 less than or equal to 0. So, you will have x 1 plus x 2 minus 1 plus the whole squared. Okay. And finally, you have x 2 greater than or equal to 0, which means minus x 2 less than or equal to 0. So, you have minus x 2 plus the whole squared. Okay, I will write it this way. Okay. So, this is going to be q of x comma gamma. Okay. So, let us start writing down the code. I mean, since we have we have written the code for quadratic penalty function when you have equality constraints. So, we can copy it down and start changing it. Okay. So, yeah, this was for when you have one equality constraint, and this was the method when you have multiple equality constraints, right. So, let us copy this down and modify it so that we actually get the code for the inequality constraint. So, let me first write down the text. It is quadratic penalty method for inequality constraints. Okay. Yeah. So, yeah, f of x is half into, so I write it as 0.5 into x of 0 minus 3 the whole squared plus 0.5 into x of 1 minus 2 the whole squared. Okay. And this is g of x is what we are representing for inequality constraints, right. So, that is going to be x 2 minus x 1. So, x of minus x of 0 plus x of 1 is the first constraint. The next one is x 1 plus x 2 minus 1. So, x of 0 plus x of 1 minus x of 2 minus 1, and the next one is minus x of 1. Okay. So, these are the three constraints, and grad g of x is just so you have minus 1 comma 1 and 1 comma 1 and 0 comma minus 1. Okay. So, okay, I think I forgot to put this, yes. Okay. So, the derivative of this is minus 1 comma 1, that is what you have here. Derivative of this is 1 comma 1, that is what you have here, and for this the derivative is 0 comma minus 1, that is what you have here. Okay. So, now q is slightly different. So, I mean we put this nice method for instead of writing, so when you had equality constraints, instead of writing h1 squared of x plus h2 squared of x plus h3 squared of x and so on, right. I mean that is too much, right. So, we got a method where we said we can just write h of x dot h of x, right. So, here there is one more issue. So, you multiply it as such only when the corresponding g of x is greater than or equal to 0. If it is less than or equal to 0, you will have to substitute 0, right. So, there is a way as well. I would like to write it this way. So, let me explain what is going on. Okay. So, I have written g of x greater than 0 into g of x. So, g of x is a vector, it is 1 cross 3 vector, a 3 dimensional row vector, right. So, when you write g of x greater than 0, this just gives you a 3 dimensional vector which either consists of zeros or ones. Okay. So, if so consider this as g1 of x, g2 of x and g3 of x. So, if g1 of x is greater than 0, it gives you 1, otherwise it gives you 0. If g2 of x is greater than 0, then it gives you 1 or it gives you 0. Similarly, g3 of x is greater than 0, it gives you 1, otherwise it gives you 0. Okay. So, just to let you know what is going on, I mean I will write this in a new tab just to give you an understanding of what is going on. So, let me define g as 1, minus 2 and 4. Okay. So, let us see what is g of x greater than 0 into g of x. Okay. Yeah, I mean I should have just written g and not g of x. Yeah, so that was because I put g of x. Okay, I have to define this as numpy array. I do not know if I imported. Yeah, so I will import numpy. Okay, so these are numpy, and this is np dot array of this, and yes, I think now you can print this. I will also write it as print, it works even otherwise, but it is okay. Yes. So, what has happened when g is greater than 0, it has given us 1. So, 1 into 1 is 1, and when g is less than 0, this is false. So, it gives 0. So, 0 into minus 2 is 0, and similarly when g is 4, 4 greater than 0 is 1, that is true, true is 1. So, 1 into g is 1 into 4 is 4, right. So, I mean this is like an indicator function. Okay. So, if for example, if you want me to print g greater than 0, okay, yeah, you can see that it says true, false and true. So, when you multiply it with g, when you multiply it with anything, I mean this is considered as true is considered as 1 and false is considered as 0. So, you are just multiplying, you are doing an element wise multiplication of two vectors. One vector is 1 0 1 and the other vector is 1 minus 2 4, because of which you are getting 1 0 4. Okay. So, this is like element wise multiplication of 1 0 1 and 1 minus 2 4. Okay. So, I think this is I mean in case you have not seen this, this would be useful. Okay. So, now coming back to what we were writing. So, what would happen if I write this? So, this g of x greater than 0 into g of x. Okay. So, this is going to give me a 3-dimensional vector, and for whichever g of x greater than 0, it is going to give me g of x. If g of x is less than or equal to 0, it is going to give me 0. Okay, and that is exactly what I want, right. And here, yeah, so here also you can write g of x greater than 0 if you want, but it does not matter. I mean even otherwise it is going to give you the answer that you want. Okay, fine. So, we will use the same technique here as well. Okay. So, yeah, this would have in general been just g of x at grad g of x, but since we want I mean g of x as g of x greater than 0. Okay. Yeah. So, yeah, that is how you have to write, and yeah, f of x, the grad f of x is different, it is np dot array of x of 0 minus 3 comma x of 1 minus 2. Okay. Yeah, so this is going to be the same, it is just 2 gamma into g of x into del g of x. Okay. And here yeah, so this will be I of 2. So, yeah, when you differentiate this, it is just 1 0 0 1. So, that is I of 2, and here you will have 2 into gamma into grad g of x and grad g of x, but here again I will multiply using g of x greater than 0. Okay. Sorry. Yeah. Okay. All right. And so, yeah, we will start with 3 comma 2. since we are finding the distance from 3 comma 2, right. And yeah, so this code is going to be the same. Yeah, we will have to remove x of 2 because this is only a 2 dimensional optimization problem. Yeah. So, let us check if we are getting the answer as 1 comma 0. Okay. So, gamma is over 2 million. So, that is actually 2 power 21. So, we have got it in the 22nd iteration, and you can see that it is the answer is 1 comma 0, and yeah, the stopping criterion is satisfied when it is 1 e minus 6. Okay. So, yeah, you can see that yeah, when you use Newton's method for solving an inequality constraint problem, a problem with inequality constraints, right. So, you are actually getting the answer, and I mean, so please recall that the Newton's method could have a problem because the Hessian is actually not well defined when gi of x is equal to 0, right. But nevertheless, we had no issues in arriving at the solution, right. So, in case you feel that, I mean, in case it turns out that the Newton's method is not giving the right answer, I mean, Newton's method can fail for many reasons. If you recall your lectures from week 5, you know that the reasons why Newton's method will fail, right. So, here there is one more reason as well. Yeah, they can fail for those reasons, and one more reason why it can fail is that yeah, the Hessian matrix is not well defined when gi of x is equal to 0. Okay. So, so yeah, in case you do not like Newton's method, or in fact it gives an incorrect answer, or it fails to converge, right, it may diverge also, right. So, you can use other methods, like for example the steepest descent, starting from steepest descent, or you can also use the conjugate gradient method. Okay. So, I will work out this code even using the steepest descent method. Okay. So, yeah, I will do that right away. So, I will just change this code whatever we have here. Okay. So, the initial definitions are going to be the same. Okay. X and gamma are also going to be the same, the first loop is going to be the same, the second loop condition is also going to be the same, but here instead of Newton's method I am going to replace it with the steepest descent method. Okay. So, that is going to be the following. So, we have to define alpha C1 and rho, which is, I mean, let us say 1 0.8 sorry 0.75 and 0.8, which is what we usually define. Then you check for the Army-Host condition, which is f of actually q of x plus alpha into del q. Actually, it is so the direction is the negative of del q, right. So, that will be minus, so I can put minus here, minus grad of x comma gm, right. So, this is x plus, and you have to write comma gm as well. Okay. Minus q of x comma gm, it should be, I mean, it should be less than or equal to. So, you do this until this is C1 into alpha into grad of x comma gm dot grad of x comma gm. So, you can put a minus because yeah, the direction is a negative. So, you write alpha into equal to rho, and yeah, so this is going to be, so you have now found the alpha. So, you have x equal to x minus alpha into grad of x comma gm. So, let us comment this out. Okay. and let us check if you get 1 comma 0 for this problem as well. Okay. So, you can see that this is actually working very slow, that is expected, let me tell you that, because for high values of gamma. So, you can recall where I mean when does the steepest descent work very slow, right, when the condition number, that is the ratio of the highest eigenvalue to the lowest eigenvalue of the Hessian matrix, right. So, if it is very high, then yeah, the steepest descent method is very slow, and it turns out that when gamma is high, okay, yeah, the condition number is very high as well. Okay. So, the way to correct it is, so instead of 1 e minus 6, we can give a smaller tolerance. I will give 1 e minus 2, okay, because I mean we are actually going to work with very high values of gamma, right. So, we have got 2 power 21, that is like 2 million, right. So, let us work with just 1 e minus 2, okay. Yeah. So, yeah, fortunately we have got the answer, and yeah, so that is again the same value of gamma, and you have 1 0 as the answer, but you can see that for each value of gamma you have so many iterations that are being carried out. Okay. So, that is very clear from the record that you are seeing here, right. But instead, if you had used Newton's method, which I mean I will like to remind you what happened. Yeah. So, each of the gamma had at most one iteration, right. Okay. So, this is 1 e minus 2. So, I can even put 1 e minus 6 if you want, and for Newton's method you can see that it is at most one iteration for each value of gamma, right. So, yeah, that is actually you can say a drawback of using gradient descent. I mean that is something that we have seen, I think, in week 3 or week 4, right, that when the condition number is not close to 1, right, the farther away the condition number is from 1, the higher the number of iterations that you have in the steepest descent method, right. So, but that is not an issue with Newton's method. Newton's method has other issues. Okay. So, you can use one of the methods, and I mean based on the application you can choose the method that works well. Okay. So, yeah, we will end this lecture here, and we will continue with the quadratic penalty method in the final lecture of this week. Thank you.